Hey everybody, and welcome to our second video in our probability unit. This video is going to be talking about how we write probability. There's a language, just like in Spanish or just like in math, there is a language specifically denoted for probability. So we need to be familiar with these terms. Some questions that we're going to be asking ourselves throughout this video is, how do we write things like this or this? Like, what is the probability that I will flip a heads or flip a tails? Alright, now what about and? What is the probability that I will draw a red card and a heart? Okay, like in a deck of cards. And the third one, the key word is not this. So what is the probability that I will not roll a 6? So we're going to be looking at these different things. Now, if you take a look here, this P parentheses A means the probability of A. So when we have functions, we talk about the function of X. Well, in probability, it's technically in the same format, but with different letters. We will say the probability of A. Now, it is important to remember probability must be between 0 and 1. There is no other choice here, okay? 0 is really 0%, and 1 is going to be 100%. Okay? So a little sloppy, but you understand what I'm going through here, okay? So we cannot have more than 100%. You can't be 110%. No. It's either 0 or 100 or something in between. You cannot be less than 0, you can't be negative, and you can't be more than 100. So remember when we talked about and or, the questions that we were going to be asking ourselves? Take a look at this. First off, this is the probability of A, and then there's this symbol here and B. This symbol actually stands for and. So if you need to make a notation somewhere, that symbol stands for and. Okay, let's erase these. Now, if we're taking a look at the second one, it points up. That one stands for or. So this right here means or. Now, the way that we read this symbol, this little U shape, it actually means the union. Okay? And the way that we read this shape here, the downward facing U, or kind of like an N, is intersection. So as I read this little math right here, I would say the probability of A intersection B. And for this one, it would be the probability of A union B. Now you have to remember that union means or, and that intersection means and. That is for you to remember. Now, recall in our last video that we talked about sample space. Remember that the sample space of rolling a die was 1, 2, 3, 4, 5, 6. The sample space of flipping a coin was either heads or tails. So basically, the probability of anything occurring in my sample space will always be 1. That's because the probability of me rolling a 1, a 2, a 3, a 4, a 5, or a 6 on a die, on a six-sided dice, is going to be 100%. The odds of me, if I take this coin and flip it, the odds of me getting either heads or tails is going to be 100%. There's no other option than the options in my sample space. There's no other events. So we can actually draw sample spaces using Venn diagrams. So it may have been a while since you've seen Venn diagrams, but let's take a look. First off, we have a circle here that's A, and I've colored this red. And then I took this circle B and I colored it blue. You'll notice that the two circles overlap and created purple. That's because when red and blue overlap, they create purple. You'll also notice that we have this big gold box. Okay, this box right here shows you every possible sample space. So every event that occurs in my sample will be somewhere in this box, either in the yellow, neither A nor B section, in the blue B section, the red A section, or the purple A and B section. Alright, so let's come up with an example to help us figure this out. Alright, so let's say that circle A are the number of students that play basketball or football. Circle B is the number of students who play basketball. And this gold box is all the kids currently in the classroom. Okay, so in our class we have approximately Let's go with 28. That's the numbers that I have worked out, although I know our numbers are a little bit higher than that for now. So let's say that 2 kids play football. We have 1 kid who plays basketball. Let me go back and fix that too real quick. 2 kids that play football, 1 kid that plays basketball. This purple section A and B means I play both football and basketball. So let's say that there are 2 people who play both sports, and then the rest of the people play neither sport. They may play soccer, they may play lacrosse, but they don't fall inside the basketball and football. Okay, so they would be considered neither football nor basketball. So we have 23 people. So if I were to take a look and count, I have 23, 24, 25, 26, 27, 28. So my total sample space includes 28 students. Okay? Now, if I want to find out the probability of A or B, the probability that a student plays football or basketball, I'm going to use this formula here. So what this means is that you're going to take the probability of all the students playing football, and you're going to add the probability of all the students playing basketball, but notice we're going to have to subtract the A and B. We're going to have to subtract this purple section because here's why. Currently, there are 4 students who play football, 2 who play only football, and 2 who play football as well as basketball. So that would be 4 out of 28 students. If I look at the people who play basketball, there are currently 3 people in the classroom who play basketball. 1 who only plays basketball, and 2 that play basketball and football. You'll notice that I have counted the people who played both sports twice. Basically, think of it this way. If you're sitting in the classroom and I asked everyone to raise their hand who played football, 4 people would raise their hand. I tell them to put their hand down, and now I want people to raise their hand if they play basketball. 3 people raise their hand, but you'll notice 2 of the people raise their hand twice, once for football and once for basketball. So because they raised their hand twice, we actually have to subtract them. So what we have here is we have 4 people out of 28 who play football. We have 3 people out of 28 who play basketball, but we need to subtract the people that we accidentally counted twice because they play both sports. So subtract 2 over 28. So the probability that you either play football or basketball is going to be 5 out of 28. Okay, so the probability of A union B, okay, is going to be 5 out of 28. All right, so now we have another word here, disjointed or mutually exclusive. These words are synonymous, however, you have to figure out what they mean. Now, disjointed, if you think of a disjointed, like if you dislocated your shoulder or something like that, they would obviously not be connected like they're supposed to be. Mutually exclusive means the same thing. We do not overlap. And the way that we would draw this is in the Venn diagram form. You'll notice that my circles A and B do not overlap. They are disjointed, and this is different than the previous page where they overlapped. So if I take a look here, the probability of a student making A in geometry is 0.28. The probability of a student making B in geometry is 0.33. So the question is what is the probability of A union B? What is the probability of A or B? So if we go back over here, probability of A plus the probability of B minus the probability of A and B. So the probability of A is 0.28, the probability of B is 0.33, and then I would subtract the probability of A intersection B. The only problem is that with mutually exclusive or disjointed events, they don't overlap. So what you see here, this is actually 0. So we add 0.28 and 0.33, and I get 0.61. That's the probability of making either an A or B in geometry. So you can see that when the 2 events are disjointed or mutually exclusive, the formula just leaves off the subtraction of the probability of A intersection B. Alright, so let's take a look at these examples. I have a question. Are these events mutually exclusive? Being never married, married, widowed, and divorced. Okay, the answer to this is yes. You cannot be both married and not married at the same time. So the probability of being married is going to be 0.622. What is the probability of being never married or divorced? Never married or divorced, we're going to add those two, and because they're mutually exclusive or disjointed events, I can just add them. There's nothing to subtract here because you can't be both never married and divorced. Okay, the whole premise of being divorced is that you were married first. So all we do is we add those two probabilities and get 0.373. So taking a look at these two disjointed or mutually exclusive events, the question is what is the probability of their intersection? What is the probability that I'll both make an A and a B in the geometry? And the answer is actually going to be empty set. So the question is can A intersection B be anything but empty set for mutually exclusive events? And the answer is no, because mutually exclusive or disjointed events will never intersect. So the intersection will be empty set. All right, here we're going to work on an example problem where we draw a Venn diagram for the following survey. So the first thing you need to do when you have a Venn diagram is to go ahead and create a box for your sample space. So these are going to be all the students polled. Now I take a look at the problem and it says that they are asked their favorite cafeteria food, nachos, pizzas. Okay, there is a nacho and pizza were tied, so that would be an overlap there. That means that these are not mutually exclusive. So we will have pizza and we will have nachos. So according to the problem, we had 12 people who liked nachos. We had 3 people who said pizza. 4 people who said both nachos and pizza, and 1 person who said neither. So this is the Venn diagram to fit this problem. So using this Venn diagram, let's answer a couple of questions. What is the probability that a student said nachos? So the probability that a student said nachos is going to be 12 out of 20, which is 0.6. The probability that a student said pizza is going to be 3 out of 20, or 0.15. Remember, probability is between 0 and 1, so not 15%, it's 0.15. The probability that they said neither is going to be that 1 person out of the 20 we polled, and that's 0.05. And the probability that a student said nachos and pizza, so the probability of nachos intersection pizza, is going to be the 4 that said both were tied out of 20, which is 0.2. Now, some of you are probably wondering where the 20 is coming from. Okay, if I go back and look at my Venn diagram here, I notice that I pulled 12 plus 4 plus 3 plus 1. So we have 12, 13, 14, 15, 16, 17, 18, 19, and 20. We have polled 20 students. That's why the bottom number is 20 for all 4 of these probability problems. All right, and the last thing we're going to talk about today is complements. Sometimes you'll see something like this where it's A with an exponent of a C. That C means a complement. Basically, it means everything but. So if the odds of me liking pizza, or excuse me, liking nachos is 0.6, then the odds of me not liking nachos, that is my favorite, would be 0.4. And the way you would get that is simply 1 minus the probability of what you're looking at. Okay, so the complement of not having an A in geometry is having an A in geometry. If the probability of having an A is 0.28, what is the complement of that? So that would simply be 1 minus 0.28, or 0.72. All right, so going back and looking at our marital status example, what is the probability of not married? So what we have to do here is we look at these are the people who are married, so you simply do 1 minus 0.622. and you get 0.378. If you were to add the never married, widowed, and divorced, you would get the same number. Well, that's it for today. I will see you guys later.